of star.
I'm going to let you set this up. I haven't been in this spot for a while. How long has it been, Frank? How long has it been, Carol? Whenever Carol started, that's when I ended.
I think you were, oh, let's see, maybe 2006?
Yeah.
When
So
you went?
this is the real name of the talk. I pondered exactly what would be interesting to talk about for the group. Dave asked for something a little bit non-technical. There are only 4 equal signs in this presentation, so it's a little less complicated than the last time. At the same time, if anybody is unhappy with the level of detail, the last presentation is still here, and I could always go into explaining population 3 stars and why they explode and make oxygen. But I thought it would be more interesting to talk about how stars evolved in human understanding. We've been looking at the sky since, well, like long before anything was recorded. What did we learn, and how have things changed to where we are today, where we actually think we got a pretty good idea what's going on? Maybe. Okay, let's see. Where do I? Okay, get this in the screen and it works. Do I have to be in the?
I think you got to scroll to the right.
Okay.
Then click there.
Yep. There we go. So we're going to talk about ancient astronomers to start with, how things changed in the Renaissance, followed by the scientific revolution, and the rise of mathematics as a description of the world. And then we're familiar with the 20th century and a little bit of the recent past. And we do have an awful lot to look forward to, and I urge you to come next month to find out. Okay, so Stone Age observatories were found everywhere and around the world. Stonehenge is extremely well known as one of the oldest, but there were also very similar observatories aligned to stellar positions in the New World as well. Humans have always been interested in the sky, at least partially because it tells them when to plant crops. Okay, it tells them when to do things is when stars rise, and that's very common in many ancient calendars. The Greeks at least started writing down what they were thinking. We don't know what the ancient people were thinking. We kind of deduce it from how things are arranged. But of course, the Greek language has survived, and they did an awful lot of neat stuff. Their big thing is they used observation as a basis to understand what was going on. And of course, still got a lot wrong. The big thing that came out from an astronomical standpoint was more of a philosophical issue, that Aristotle believed in perfection and the skies were perfect. So everything had to be circles. Okay, as we know, that's not true. Yeah.
Would you mind minimizing the window in the upper right? It's covering up some of your slides.
I have no access to that here. There's, and let me just go back. Yeah, there you go. So, they thought orbits were circles. The sun was in the center, the Earth was in the center, and then by the dawn of the Christian era, I guess you could say, Ptolemaic model added a way to deal with planets. But they were all a little wrong if you ran them far enough. Okay. And all they were looking at was positions of things. Okay. That's all they could. And for a long time, that's all we had. Copernicus, Brahe didn't have the advantage of Galileo's telescope. And honestly, Galileo's telescope didn't teach us a lot about stars per se. That would take a few hundred years to happen. But these people did change our place in the universe by making it clear that we're not in the middle of everything. The sun is in the middle. Of course, that was kind of controversial at the time. So people tended to hang on to things until they were about to die and then try to pass them on to someone. So Copernicus only published in late in life because he knew he was dying. Brahe only gave his data to Kepler after he died. But these folks got the sun in the right place, and doing that took care of the retrograde problem. Okay, explaining the planets. That's what I got here. Brahe figured out a solution. And we know it as Kepler's laws of planetary motion. Okay. There's an equal sign. So, okay. The key here was we were starting to use mathematics to explain the physical world. Galileo provided additional observations. The moons of Jupiter. If you have a pair of binoculars, this is pretty much what you're going to be able to see any night. Okay, it's what got me started, but little pair of 10 by 50 or 10 by 25 binoculars out in the Adirondack. So there's observational evidence for a sun-centered solar system. The other big thing Galileo did was to start using math to describe physical systems and how they worked. I would say I think of him as the inventor of physics, if you got to name one person. But in all of this, the stars are simply little points of light, little fires someplace in the firmament. We had no idea where. Okay. Then along came calculus. And calculus changes everything because now we can describe, say this properly. Galileo's laws of motion were very simple. They were empirical. He was literally rolling balls down inclined planes just to make the ball move for a longer time because his clocks were bad. Okay, he couldn't measure a tenth of a second. We just drop things and measure how long they take for each. And everybody who's done a physics lab has measured the gravitational constant or the acceleration due to gravity, not the constant. The thing Newton also did, in addition to coming up with calculus, was he started saying, and there are some fundamental physical properties that explain what's happening. Okay, and this force law is exactly the same. Let's see, do I have it? Yeah, there we go. Okay, this is exactly the same force law as you would see for electric forces, except it's a different constant. Okay, and it's the product of the two charges divided by r squared. So we now have a different kind of perfection. Okay, instead of everything having to be circles, they just have to follow some sort of law. That led to discovering a lot of physical laws that I'm not going to go into. But the key thing is that as we understood matter better, it allowed us to design ways to investigate matter better and understand it better. So we're on this upward move. The other thing is that these laws were repeatable, reproducible. Anyone could do the experiment and verify the law. So science is becoming a little egalitarian. Okay, it doesn't depend on force or dogma for what it's doing. It says, okay, if you don't believe me, go look for yourself and tell me what you get. Okay, and of course their laws are couched in mathematics, which advanced in parallel. In math, they teach you all these funny transform things and don't teach you that they are all solutions to a physical problem. Okay, Fourier developed Fourier series because he was he's working on heat transfer and trying to come up with a good theory of heat transfer that would make predictions. A lot of this culminated in Maxwell's equations, which you see in the background. But the question you should all be asking yourself is, what has all this got to do with stars? Well, you got to take an thermodynamics to gravity to see where thought went. We realized that gravity would cause things to attract and gather in one place. And if you do that, you're going to probably build up pressure and temperature is going to go up. And if your temperature goes up, now you're going to have energy Okay. And oh my God, stars shine because of gravitational compression. Problem solved. The only problem was they didn't know how far away stars were, so had no idea how bright they were. Just, you know, and this truly was inconceivable to them. So time marches on. Fraunhofer develops some special telescope instruments that allow precise measurement of positions relative to background stars, and Struve and Bessel measure parallax, find out how far away stars are. Yeah, a lot further than anyone thought. But we at least get, you know, start getting distances out to maybe 100, 200 parsecs. And at the time, this is the limit of what stars we knew. So we ended up calling, you know, so we studied them. And we ended up calling them population 1 stars because we found there was another population out there. Okay. So the stellar distances revealed intrinsic brightness. And we got a surprise. Stars are very, very far away, and there's absolutely no way a gravity-based heating system is ever going to make them shine for as long as they do. You know, it's not just that they're bright, it's that they're bright for extremely long periods of time. Then along came the atom. Bohr developed a basic model. Fermi demonstrated that you could generate energy with fission reactions. And then World War II came along, and all of a sudden we had to figure out how to make things go boom. The silver lining to all this is that the mathematics of hydrogen bombs is very similar to the mathematics of solar fusion. You're doing the same kind of reactions. So we learned an awful lot about the sun doing military work. Sad, but true. We found out what was possible. And of course, if you're not aware, you know, nobody tests thermonuclear devices anymore. Everybody models them because they're so good at modeling it. Yeah, like.
That's the fifth equal sign.
Oh,
There's
good.
only gonna be 4.
Well, no, the four on Maxwell's equations don't count because they're in the background.
And there was one, that's the fifth, not including. I've been counting.
I counted 2. We'll have to resolve this in committee. Oh. Again, the story is one of we learn stuff here, we apply it there, it teaches us new stuff that lets us learn from someplace else. That's how we got to where we are. So where are we going? How did we get here? What did we actually look at? And in the background, I have a Hertzsprung-Russell diagram. If I could find that stupid little cursor, there it is. Okay. So I'm using the cursor just so the online people can see. So we observe stars. We look at stellar nurseries, and what we find is stars. Where's my? Okay, this isn't going to work. We find stars that are very low temperature, but fairly bright, that get dimmer as they get hotter. Well, that's this big thing blowing cloud of very low temperature stuff coalescing into a very dense star at very high temperature. Okay, and that's how stars all come in from, let's see, right? Okay. The old open clusters, they branch off toward the red giant branch. When we look at stars, we see a mix of sizes. Okay, big ones, they're not too common, but extremely easy to find because they're so bright, right? But we know there's a lot more smaller stars, and we found stellar endpoints that can be spectacular. I mean, when I was born, people thought black holes were you know, yeah, that's something for sci-fi. But now we know they're real and they're all over the place. It's just amazing where things have gone. But we also found stars that didn't fit the model. Models were based on the early stars, the ones that we could see, what we ended up calling population 1. And we found some real oddities, exceptions. As instruments improved, again, we could now see we could now take spectra from new stars that were further away, and their spectra was very different. Okay, and then we also started, again, getting more and more precise, started to see wiggles in the spectrum. Okay, so it turned out these other redder stars were what we call population 2 were simply the older stars. Stars formed very early in the Milky Way's existence. The characteristic is that they're missing most of the elements above helium, the second one on the periodic table, what we call metals. And they're also missing all of the really bright stars. Okay. The odd wiggle in the spectrum signaled multiple bodies. And the first thing we found were spectroscopic binary stars. Looking at the Doppler shift, we see a regular pattern of lines shifting back and forth from the two different stars. With increasing precision and long-term observation, we started seeing small bodies. And there's no question now after what was it? I'm remembering the right telescope. Kepler was the one that was staring at a spot up in Cygnus for several years, just looking at the stars' brightness and looking for transiting exoplanets, and we found them. And we found them everywhere. There are a tremendous number of different exoplanets to date. And what they've told us is that we don't have a clue how planet formation actually works, because none of the orbits look anything like the solar system we're in. Nobody expected hot Jupiters. Didn't see it, you know. So this, you know, and the other problem we have now is that, well, had until recently, was that we were incapable of sensing anything about these planets. We couldn't see well enough. We were just getting hints of what might be in the atmosphere because of instrumentation limitations. Okay, another thing that we've done fairly recently is extend the distance ladder with supernovas. But wouldn't you know, there's a problem. We get a different answer looking at supernovas than we do from looking at the cosmic microwave background. And this was first observed, 10, 15 years ago, and recent data has not closed the gap at all. There is something going on that we don't understand because we think we have two perfectly good ways of measuring it. And if you take a look at the cosmic microwave background spectrum, the power spectrum versus not spatial frequency, but versus spatial angle, there's a region at low frequency, which is large separation, where the model doesn't conform to the data. Now, it fits a lot of undulations over a long span, but it doesn't fit over the whole thing. So there's some things that we're missing. And then, of course, we predicted that there's this population 3 kind of star that formed shortly after recombination in the era shortly after the cosmic microwave background, that were near zero metallicity and then therefore became extraordinarily large. Many ended up in black holes. Others created large amounts of relatively light elements. Okay. But we need something to figure out where the supermassive black holes in the center of galaxies came from. Okay, and that's where there's a big question. Well, we think we're going to get some answers out of this thing. James Webb, I think, is going to change the world again. Like Hubble did, this will do the same. The IR-centered sensitivity gets you into high redshift objects, allows you to look at the microwave range where a lot of elements, I should say, interact with light so that you can observe them. One of the first things they published was a spectrum of a star showing absorption peaks from water. I'm sorry, a spectrum from an exoplanet showing water. Just extraordinary things you can do with that size mirror and its location on the far Laplace or Lagrange point. Just an excellent thing. And I'm not going to say anything about it because that's next week. That's the future. I'm trying, my scope is limited to how we got here. So that's it. Now, if you really want me, I do have all the slides from the other talk. If it's too quiet for you.
Frank, when you say a population stars at zero, here's zero on the list, what does that mean?
Oh, population 3.
Population three stars.
Yeah, they were made directly from the primordial gas from the Big Bang.
So it's only helium and hydrogen.
And parts per million and parts per billion of lithium and deuterium and yeah. There's something odd in nucleosynthesis that lithium and beryllium don't like to form. Most of the lithium and beryllium on Earth were formed by cosmic rays hitting nitrogen. Okay, and aren't we lucky because there's a point in this in the nucleosynthesis of stars where you're making beryllium and it's falling apart as part of the proton-proton process. So you really don't build big molecules until you get into the CNO cycle and then the triple alpha process moving forward. CNO cycle takes carbon and builds up a helium molecule and then releases it. So the carbon becomes oxygen and then decays back to carbon and becomes oxygen again. Okay, that's the complicated talk. There's from there, if you get those heliums hot enough, they will start to glom onto other heliums. Okay, so atomic number 4, that's beryllium. That's unhappy, but you get up to 6, carbon, oxygen's 8. Okay, and every even number molecular weight has a peak in abundance until you get to iron, and where there you form silicon and then decay into iron. No, I'm sorry, you form nickel and decay into iron. That's right. So, but that's nuclear synthesis. That's born to evolution of star. The internal evolution of a star. So.
Is it possible that beryllium forms new molecules or new entities? I went into H.C. Brown at Purdue University back in 1972. Put a lot of emphasis on beryllium production. We had numerous organic chemists work with it. I was just pointing here, is there a spin-off from all that research in beryllium technology?
That's good. I don't think I put that slide in. Yeah, I can show you how we think the nuclear reactions work. Okay, I'm unaware of anybody who's trying to make beryllium because the paths that come out of the proton-proton chain are all running at 10 to 15 megakelvin. Okay, I mean they're fusion. It's the kind of temperatures the National Ignition Facility is trying to reach.
A lot of things going on since that time in beryllium, because most of the organic chemists used beryllium for medical purposes and new compounds.
I have a request for our folks that are here on Zoom. Could we re-angle the mic so it's a little closer to the audience and that way we can hear the questions?
I'll be happy to when the audience talks next. So, Mike.
Use an analogy with large stars like DY Canis Majoris, which you can use like I forget if it's the orbit of Jupiter or the orbit of Saturn that it's kind of comparable to. For the population 3 stars, does anybody here know how big those would be? So if we use the analogy of our solar system.
In size? No, they're not large in physical extent. They're supermassive, 100, 2, 3, 500 solar masses. In fact, there's a limited range over which you actually get something we would call a star before they go right into black hole. Okay. You see, here's one of the things that makes.
So let me turn the question around. How many solar masses?
Like I say, I got a nice chart showing you the endpoints. Okay, and there's Big ones go to black holes. There's a neat range where you get a positron electron pair generation in the core that results in zero residue and the spread of huge amounts of heavier elements. Okay, and then smaller ones that they really don't have it. See, here's what's different about population 3. You have hydrogen and helium. At 100,000 degrees, hydrogen becomes ionized. Okay, it is now you only need 100,000 degrees to get a hydrogen plasma. You only need about 1,000,000 degrees to get a helium plasma, to have taken the electrons and completely removed them from the okay. Those changes when a nucleus loses its electrons, it loses about a factor of 10,000 in cross-sectional area. It shrinks because the proton's tiny. And it's the electrons that are making contact whenever we do anything, right? So all of a sudden, there's no space. Okay, everything can get very dense. And if radiation is generated, it's got to hit a really, really tiny target in order to cause any outward pressure. Currently, we have stars that are designed such that the outer parts retain their electrons, have clouds, are hit by photons, and that pushes them back so that we get an equilibrium between the radiation pressure and the force of gravity. And in those early stars, there was no parachute for the photons to hit. They had to hit nuclei, and the odds are much lower, so these things just started coming in really fast. And you didn't have to get too far to get ionization, so the cores would have been huge in terms of the plasma. Okay, and once you hit 10 million degrees, you're starting to run the proton-proton chain, because the helium nuclei are the hydrogen nuclei have enough, the protons have enough kinetic energy to actually merge together for a little while. Okay, and that's a whole bunch of other stuff. So does that kind of make sense? This is the thing that got me started on the other talk, was thinking about liquid, solid, gas, and plasma. And plasma is so different. Yeah, Mike?
You've been telling us quite a lot about population 3 stars. Have we ever seen?
No.
Okay. Can you tell us about other things we haven't seen?
I'm answering questions.
What about pink unicorns?
Yeah, it's just that there are a whole bunch of papers back in 2005 when they were trying to get funding for James Webb that talk about exactly what they think they're going to find. But until they look, they don't have a clue. Okay, and we're just starting to look because, I mean, gravitational lensing helps. You'd like to do direct observations. This is complicated. So Mike's got a lot of job security. So. But there's some aspects of it that are easy to understand, and one of them is that our curiosity leads us to ask questions, and those questions invariably lead to other questions. And as long as we keep saying, oh, and how can we make our instruments better so we can get more data, we're going to keep finding out new things. And James Webb is just the latest big step. So I mean, Hubble wasn't that big. Hubble's a 2.5 meter telescope. Okay, that's Hooker. That's Mount Wilson. Remember, about 100 inches. Is my math about right? We were there 100 years ago from a light capture standpoint, and thankfully it's a good mirror. But that 2.5 meter telescope led us to Hubble's law. Okay, Hubble's Space Telescope 2.5 meters led us to, well, God knows what this is going to lead us to. Questions? Did I take up enough time? Honestly, I
mean, I wouldn't mind at least seeing your more detailed presentation.
Sure.
Or
well, I can go
any
into
specific highlights that.
Well, okay. End slideshow. That's what I'm going to do. You see, I keep going, but I hit everything. Now, Control A. I want unhide.
You know, Frank, what's the lightest metallicity star that we know of?
There are some. Mike could probably be able to tell you more than I could. I'd have to look it up.
The stars we've observed in the Milky Way galaxy that have the fewest heavy elements have roughly, I think, about 1 part in 10,000 as many carbon, oxygen, iron as our sun. So a factor of 10 to the minus 4 times the solar metals. I think that's about the current number. And people have discovered the record holding these metal rich stars in the last few years. People are looking hard for them, and you'll probably hear about new discoveries. Probably not with JWST, but with other telescopes over the next few years. So maybe we'll find one that's 10 to the minus 5. But still, we haven't found one that has absolutely no heavy elements.
Mike, where are these stars? Are they must be in more pristine portions of the galaxy that were never enriched, or where are they?
If you made it a long time ago, it can just cruise around in the galaxy and it won't pick up dust like socks under the bed.
Well, it does, but it does pick up some.
Not enough to really make much of a difference, I would say.
Well-
We find them in random places in the galaxy. They're not all clumped together in one place. They're all.
But they're old, not necessarily just in some
They're
cleaner space.
individually old stars, one over there, one over there. One over there.
And I think there is one place where we have found like conditions where they're actually forming new stars with low metallicity. And I'm blanking on the.
Is it a globular cluster?
Yeah, but it's a globular cluster that's forming now. You know, globular clusters we thought were formed 13 billion years ago. Or so. So if you want to get into the rest of it,
I'd like to share that.
I'm sorry.
I'd like to share that with the people online.
So we're not sharing. How do I tell?
Yeah, we can see it
Sure.
online.
Yeah, we can see it.
Okay, yeah, because I didn't close PowerPoint. So, but yeah, the differences between hydrogen and helium in the metals. Here's hydrogen and helium radius in picometers. Milli, micro, nano. Is it pico femto?
Nano picofemto.
Okay, so we're like 10 to the minus 15th, 18th, 18th. Yeah. Okay, so really small. And that's the atomic radii. That's the electron clouds. Okay, and as you can see, and all we're doing here is showing you the electron valence electron shell structure. Yeah, this is a 1s. This is a 2s. These are 2 p's, 3s, 3 p's. Okay. So the size of the electron cloud varies. It's only a quarter of the size of lithium, half of the CNOs. And the first ionization is really easy. This is in electron volts, but I try to put it into megakelvins. Okay. And contrast the fact that oxygen requires 10 megakelvin temperatures to ionize, where hydrogen only needs a tenth of a megakelvin. Okay, which is, we were talking about a little bit before. Okay. We saw 2 populations of stars. It varied by the abundance of atoms heavier than helium, we called metals. Population 1 are found in the disk, metal rich, relatively young, close to Earth, because we're in the disk. Population 2 are mostly in the halo, the spherical bulbs, the metal core. We think they're the first generation. And this is an idea of what the spectrum looks like. Okay, pop 1 versus pop 2. As you can see, it's just missing a lot of stuff. Okay. And today, oxygen is the most abundant metal in the universe. I was very surprised to learn that. So you see some iron and nickel in all of them. So how do we define it? I think I'll get to that. This is what we were talking about a minute ago with the needing to have elements that hold their electron clouds in a star in order to have the photons press against something to get this equilibrium. Okay, where the pressure of gravity pushing in is balanced by the pressure from the energy released by fusion pressing out. Okay. So we got hydrogen and helium fully ionized, form plasma. Plasma is a mix of bare nuclei. And I talked about that a little bit ago. That they're much smaller. And what happens when gravitational collapse meets little opposition? That's the key in my mind to the population of stars. This is a kind of generic diagram showing how star size changes the internal structure of stars and changes the reactions going on inside. I brought along a couple of things. Anybody get Sky and Tell? You should have seen a similar diagram recently. Okay, on the article about white dwarfs. I will note, however, that these are missing a core.
Do you want to show people online?
I'm sorry.
Do you
Oh,
want to show
yeah,
people online?
that's right. The most recent Sky and Tell? No, it's not. No, this is December. Sorry. Get the right page. And there's the little diagram, which looks a lot like what's up on the screen. Okay, my point being, if you want to learn about this stuff, astronomy magazines are not a bad place, because they'll not only tell you what's happening new, they'll also go over what happened in the past. That's why I brought this one. Anybody ever hear of Wolf-Rayet stars? Okay, really neat objects. Good article. Okay, they're one of the exceptions to all of this. So, yeah, this is just looking at the idea that the smaller stars don't have enough mass to get the temperature in the core high enough to go past proton-proton. You need to get to about 15 megakelvin before you get CNO started. Okay, but CNO is perfectly adapted for large stars. It's got a great feedback, negative feedback, where if the temperature is up, the energy output just skyrockets. It's neat. Okay. Okay, we know that. And then just talk about smaller stars, proton, CNO. Now, how does proton change? Temperature is usually dominated by CNO. That's where this talk is going for population 3, where we don't have any. So we got to go back to what survived the Big Bang. Okay, and this is a chart trying to show in mass fractions rough amounts as the universe cooled. And these are megakelvin. Yeah, no, these are gigakelvin. These are billions of degrees. Okay, but we're also 100 seconds, 1,000 seconds after the Big Bang, a long time ago, showing just the prediction for helium-4 and hydrogen. A lot of that showing up at the top, and then much lower. You'll notice that you don't get to something besides hydrogen or helium isotopes until you're down at 10 to the minus 10th. Seeing some beryllium and lithium. Okay, so this is what we think these primordial stars were made of. Like I say, nothing but hydrogen and helium. You know? So this would be one definition of zero metallicity. Okay, what we're seeing is, Mike, you were saying something like you were saying like 10 to the minus 4th less in the low metallicity stars.
Yeah.
Yeah. And is that a mass fraction kind of thing that's comparable to this kind of scale, or are you looking at something else?
Gosh, I don't know if it's a number fraction or mass. I guess it's a number fraction.
That could do worse. Yeah, you're right. No, that's what most of them are. If you look at the mass fraction, it gets really bad because Helium may only be like 4%, but it's 25% of mass because the heliums are so much bigger. It's crazy. So also had to look at cosmological redshift and distance. Mike, you still counting equals yet?
That's not.
Yeah, eight just on here. And the thing that got me was the vacuum densities. Today, the intergalactic medium of 40 atoms per cubic meter. The interstellar medium, 1 million per cubic meter. Okay, we don't think of the interstellar medium as being a poor vacuum. It's an extremely good vacuum, but not compared to what we get on Earth. So, okay. Oh boy, and I get into genes mass here too, which I don't want to get into too much. So this is a quote from the Scientific American paper, December 2001. Okay, computer simulations show that they should have appeared, but again, this is all simulations from 20 years ago. Hopefully, we're going to find out the answer. Okay, this is the one that shows all the reactions. The 3 different proton phases and CNO, if you want to know the detailed steps that happen in each one. Lithium and beryllium. Okay. They form and fall apart. Okay. In Big Bang nucleosynthesis. So the other thing I want to point out that's particularly significant, I think, is the rates. Proton, it goes by temperature to the 4th power. Okay, you double the temperature, you get for 16 times more energy. Right? You go to CNO, it's 17 is the exponent. You go double that, you get for 863. Say 10 would be 1,000 times. It goes up really fast. And what that does very nicely is moderate the gravity by putting out huge amounts more energy if you just put a little bit more force on it. Raise the temperature just a little bit, you get a lot of energy, and that's how giant stars are balanced. Okay. You go over to triple alpha. Now, this is what's happening as stars die, and obviously you've got a much even higher. Because the idea is that most of the heavier elements are simply helium nuclei grafted onto whatever nuclei they can find. Okay, so now, this is important. Proton cannot form carbon. That's what that little thing is covering. And therefore, if you need carbon to start triple alpha, you can't do it in these 1st generation stars. If they actually even show it. You want to go into this? What's happening inside the nuclei, this is not the same as in today's stars. Because today's stars don't have the temperatures to get to antimatter. So I'm not going into it. And you wondered about what happens. This is today's stars in terms of stellar mass along the x-axis and the remnant mass on the vertical axis. So one is the x-axis is how the star grew. Y is what's left after it transitions. Okay, and you can see there's a line for no mass loss. Okay, for relatively small stars, and interesting things start to happen when you get into the neutron star and the black hole ranges, depending on the history of the star, because today is complicated. This is the one for the primordial stars with zero mendelicity, or at least this is what the papers in 2005 were predicting. I did cite the paper. And that is that you get up to about 30 solar masses and you go right to black hole. You have a little range in the 150 to 300 range, where those are they're supernovas that have no remnant, because the supernova is caused by a antimatter explosion in the core. Okay, once it starts to expand, you've got an awful lot of matter that will not produce radiation until it annihilates, and then it'll produce a ton. Okay, and then as you see, the larger and larger black holes go right to direct to black hole. So this is kind of what's predicted. Yeah.
I thought the supernovas were supposed to shrink in stars and they explode.
These are very different stars.
Oh, okay.
They probably will not go supernova because they will never form iron in their core. Okay. They're too big. Okay. Forming iron in the core is kind of like supernova, or I'm sorry, planetary nebula sized stars. Our sun will form a planetary nebula. You go look at Betelgeuse, that's going to be a supernova. It's going to make a nice planetary, but there's going to probably be a boom at some point because it's so much more massive. Okay. These are 10, 100, 300, 1,000. I mean, it's a log scale. So the size gets very large, and after a certain point, they think they're just going to form black holes directly, which is good because, again, the fundamental issue is we got to form multi-million solar mass black holes at the core of galaxies, we think, for the galaxies to form the way they do. And we don't have, we have theories of how that might happen. Okay. And again, this is looking 17 years ago, because, yeah. Yeah. The pair instability supernova is just a neat idea. And everybody gets onto that. But they have one real big positive benefit. This is what they think comes out of the explosion that results in no remnant. Yeah, 45% of the star's mass is turned into oxygen. Know where the oxygen came from. Okay. Lots of other, not a lot of carbon, but it's almost like it jumps over carbon at atomic number 6 and hits 8. Let's see, what's 10? No, that's so 12. Yeah. Got some silicon, but anyway, this is what they're predicting. And so a summary. So we think first, the first stars should have had very, very low metals. We don't know, haven't measured it. Okay. That lack of metals would hamper the cloud cooling and drive up star size. You get high density. Gene's mass has to do with coalescing of interstellar media. I don't want to get into that. But with no metals, they had no way to oppose the inflow of matter once you got up to about 1 million degrees, and helium was ionized. So, proton-proton reaction is not very temperature sensitive. So as it got hotter and hotter, it did not run faster and faster. In fact, there's a point. Oh, let's see if I can go back to it. Yeah. This is where everything goes to hell, because 25% of the energy starts to go out in neutrinos. Okay, neutrinos do not interact with matter. So what was already very inefficient just dropped by a third. And that really changes things, because there's even less energy pressure opposing the gravitational collapse. And I suspect that's when everything gets interesting. So, okay. Okay, and that's it. So this is kind of my understanding of what exactly happens at the end. And eventually, antimatter core disperses everything. If it doesn't form a black hole first. So you've now gotten both. That's bad. Any other questions?
Theoretically, as the galaxy ages, there be eventually nothing but black holes left? Like,
Good question.
Frank,
Please
could you-
repeat the
could you re-
question.
Could you repeat the
Thank you.
question because we did not hear it
Yep.
online?
The question is, as time goes on and things keep accreting, are we going to end up with nothing but black holes left? Is that a fair way to say it? Yeah. And the answer is no, because we think the universe is expanding too fast for them to find each other. Unless we're wrong and it's not expanding that way. You're right. That question fits right in the nexus of this funny stuff called somebody help me. I'm losing. Sorry.
Dark.
Dark energy. That's it.
Fuck, man.
You see, what we've discovered is our universe is 6% stuff like us, 25% dark matter, which at least has gravity. Okay, we know it's there by its gravity, but we can't find it. And then 70% is something we don't understand at all. But if we don't put it there, the models come out wrong and don't agree with the data. And we call it dark energy, and it can really mess with things.
okay. Change my question a little bit.
Sure.
So as the universe is expanding, will the center of the universe eventually just be black holes, and it's just like a rim, a ring of newly forming stars like being chased by?
So will black holes form in the center and just propagate out as the universe ages? No, because every place in the universe is the center of the universe. This is one of the funny things about that makes it hard to understand Big Bang cosmology, is there is a point we call inflation, where over a short period of time, before there were things like mass, or they could slow it down, the universe expanded by more orders of magnitude than we know. We know that it expanded further than we can see based on the age of the universe, the speed of light. Okay, so, and this also happened, remember I was showing things happening at 10 seconds, 100 seconds. This was at 10 to the minus 30th seconds. So you're past femto and any prefix. So it's really early. Okay, and that's part of the whole story of forces coalescing out. Gravity doesn't exist until inflation, and then afterward it seems like it does. As things cool a little bit more, the electromagnetic force and the strong force in nuclei start to become evident, but they don't exist early on. They have to form. And again, we're talking, okay, if I could do that, that's too long. By orders, well, by billion orders. It's hard to get small numbers. But so that's why we don't just start here and black holes propagate out. So it's all happening at once. That actually is a very interesting corollary to what happens in the core of a star that's about to go supernova. Okay, the last thing we talk about is they get a degenerate iron core, but a few milliseconds earlier it was a silicon core. Okay, and no matter how big it is, when it's exactly the right conditions for the silicon molecules or silicon nuclei to merge to form nickel and then iron, they do everywhere in the core all at once. Okay, it doesn't propagate. Okay, and there's a great example if you're familiar with gasoline versus diesel engines. Gas engines have a spark. You set in a fuel mixture that's very volatile, and then you give it a place to start, and you get wave propagation. In a diesel, you take the air and you compress it until it's well above the ignition temperature, and then you spray atomized fuel into it, and every droplet of fuel explodes at the same time. And that's why diesel's not, and gas engines don't. You're actually hearing an explosion. And it's that kind of a thing where the entire system is ready and it all goes at the same time without any time-based things happening. And that's kind of neat. So, and a lot easier to understand than the magnetohydrodynamics you need to understand plasma. Because, you know, one of those neat little things, you create electromagnetic fields by moving a charge. Everything in a plasma is charged. So every time it moves, it creates an electromagnetic field. Oh, by the way, it's already following electromagnetic fields as it's creating electromagnetic fields. Magnetohydrodynamics is complicated. So I won't go into it. Okay, so there's my black screen again. Spoken long enough. Now, see, once upon a time, we used to have 2 talks. Yeah, we have a short talk, long talk. I thought I wouldn't go on until 8:30.
One last question, if I may.
Yes, by all means.
Where are these theoretical population 3 stars expected to be found?
Everywhere. I mean, we see that, okay, where are population 3 stars expected to be found? Everywhere the cosmic microwave background is found, which is 4 pi steradians. Okay, everything.
If we haven't seen any or observed.
They're too far away. Okay, and the too far away is that they're incredible. They're redshifted just a little less than the CMB. Okay, and that's why we need the infrared sensitivity in James Webb to be able to see the redshifted energy. Okay, now all we're looking at.
Oh, wow,
yeah. If we can find some of the galaxies, we'll be really happy. Finding the stars is a whole other story. Okay, because too far. I mean, yeah. How big a gnat can you see? We can't see the flags on the moon. We're not going to see individual stars at the dawning. But what will we see? We don't know. We got to look, and that'll teach us something. And what we learn from that will inform the next step. And it's been that way ever since somebody realized that if they stuck 2 rocks in the ground, that star lined up over it at the same time every year. And it was a good time to plant crops. Or it was a good time to head for the hills because you knew the floods were coming. Okay, I mean, how do people deal with monsoons? How do people deal with climate change, which was a very demonstrable aspect of ancient history? Okay, as we've been able to take some of the paleo records of sea surface temperatures you can predict rainfall changes and where it'll occur. And that sometimes occurs where a civilization formed because they were favorable times and now it's not. This is the old lakes in the Sahara. We see channels, signs of water erosion under the sand. Ground penetrating radar is neat stuff.
Isn't there some evidence that has to do with precession?
Milankovitch cycles are absolutely part of it. Okay, we should be going into another ice age right now, but we're not. I mean, from the cycle standpoint, it's complicated. Either way, for more information, 25-year-old textbooks are still very, very good for this kind of stuff because we haven't learned that much. And okay, hang on. I am holding a copy of the 1999 Foundations of Astronomy by Michael Seeds. Okay. We have a lot of these running around the club because a lot of people do the adjunct courses and they'll always send you what we're used to. Another even better source, but it's hard to spell his name. A guy named Fraknoi, F-R-A-K-N-O-I. Fraknoi, Morrison, and Wolf is another one of these textbooks that I've used. He put his online, 12,000 pages, teacher's edition. He did not try to condense the pages. Okay, so don't be put off by the 12,000 pages as opposed to what 500 or 600 and something like this. It's online, it's free. So great place to go if you're interested in the history of astronomy, the basics of light or telescopes, or
the factoid was the name was the author was the name of the book.
Just do a search. Yeah, it's an odd enough name that you will end up with an astronomy book for non-science majors. That is to say, it's not heavily in math and calculus. Now, you have your hand up?
What is the universe expanding into? Like, if
Itself.
if you were to straight up, the sky is blue and then it's darker, darker, darker. If you were to go like just keep going straight, is there an end to it, or is it like? I've been trying to wrap my mind around it since I was a little kid.
The Hubble Deep Field is the first time we took a telescope and stared. The first images were 1,000,000 seconds, and they've gone way past that. They're going to do the same thing with Webb. Okay, and what you're doing is they took an empty piece of sky and stared at it to see what was there, and found like 1,500 galaxies. Okay, so what happens if you look is you just see further back, and in time. Further away is further back in time, because it takes light time to get there. So one of the neat things about light year being a unit of distance is it also gives you an idea how long things take. You know, Alpha Centauri is about 4 light years away. So the light we see is 4 years old when it gets here. 2.5 million years for the Andromeda Galaxy, because it's 2.5 million light years away. We're now talking about things that are 12 billion light years away. Okay, you've just gone up 3 orders of magnitude. It's a lot further away. Okay, and so a lot smaller and harder to see. And that's what ends up happening simply is as we go back, we get this thing we call redshift, where there's less energy in the light the further away it was emitted. And eventually you get to the furthest thing we can see is cosmic microwave background, which is at 2.7 degrees Kelvin. It is not at absolute zero, but you know, if it were closer to us, it would have a higher temperature because it wouldn't have to see as much redshift. Redshift is something that takes a while for people to understand, because it's literally, you know, lifting out of a well. You have this is bluer light than this because I've raised it up here, and it's higher in the Earth's potential well. Okay, time is going slower up here than it is down here. Okay, but we got to go up a few hundred miles with a clock good to 10 significant digits to be able to tell that, to actually demonstrate.
It's not something that could be contained, like if you were looking and you see Earth and it's contained, if you were to get back far enough
Away?
Yeah, would it be just like contained and then outside of that?
No, you can't see outside of the universe. Well, we think it goes on past the cosmic microwave background. Okay, now Mike's had his hand up.
Oh,
For a second.
So you're asking a question many people have asked for
Yeah.
many years, centuries. We don't know the answer to it. Some reasons for it.
Frank, can you repeat that question? Folks online were not able to hear it.
Yep, you're right. We've been doing a whole discussion without repeating the question. We have been talking about what happens if you look up and just keep going in that direction. Don't you eventually get to a point where you can look back and see everything? Is that the kind of thing you were asking?
Like if there's an end to it, like if we were to break through the ceiling, there would be something else.
Yeah.
The best guess, but it's not knowledge, is that the universe is infinite, all directions. So there is no end. But human minds don't like that. So
Yeah.
it's okay to not be upset and say, no, I refuse to believe that. It's fine.
It feels like it should come,
Yes,
like
it
there should be
does.
a point and all of a sudden it'll be like,
Yeah.
does it go back to like blue and then another?
We're having a discussion in the audience of it's the endpoints of universe structure. And then one thing I'll just say, what we see is that the cosmic microwave background is empirically the most distant thing we can sense. Okay. We think there's stuff past that, not in time, but in space, because we're seeing the CMB out at 13.5 billion light years, age of the universe times the speed of light. Okay.
So there's a difference between how far the universe potentially extends and how much of that is observable.
Yeah.
Because light travels at a finite speed. So if the universe is really big, the observable portion would be potentially really small compared to it.
Yep.
Definitely, if infinity is the size of the universe, the observable portion would be minuscule.
Not a portion of it.
Yeah.
Well, but there's a real conflict here, because on the one hand, if the universe starts as a big bang from a point and expands, it can't expand faster than the speed of light, which was the problem. It shouldn't be bigger than the center of the universe. So they came up with this inflationary theory that in the very first picoseconds, it had this geometric expansion into an area which we will never be able to see, because it was outside of our observable envelope in the very first instance, and it will be forever outside of it.
Yeah.
And no second grader I've explained that to was happy with that. The other thing they're not happy with is, traditionally when that question gets asked, one of the answers is, well, the Big Bang is not just a creation in space, but it's a creation of time. Time is just another parameter that's created at the same time in the equations. So to start talking about an area that is not in time and space, it's outside looking back, is a philosophical problem that we're talking about the created space and time and what else is there. And as Mike pointed out, that's now a whole subject of discussion. Are we part of some larger system that has micro, big bangs and maybe big collapses, whatever. But I don't know, Mike, I don't think we're there to talk about that except in theory.
Now let me ask,
Multiverse type conversation here.
can anyone hear Jim online?
Yeah, we can hear that.
Crossing fingers you can, because
I'm
I'm not,
loud enough people can hear me.
but I'm not repeating all of that.
Nope, we were good.
But it's a real philosophical problem, and I get asked this question a lot at the planetarium, and no one's happy with my answer.
Yeah.
Theoretically, if there was something that the universe is expanding into, moving beyond the realm of the universe, then that would imply that that was perpetuating. So,
Multiverse.
right, so
Yeah.
it goes back to the infinity thing. The universe is everywhere already. Like,
Well, I haven't seen, okay, again, we're getting back to how big is the universe? And I don't know. I get confused in this stuff too. Yeah, my understanding is the inflation period occurred before physical laws had actually been established. So you didn't have to worry about the speed of light because there was no mass. And energy and temperatures are so high that the energy is mixed up in matter and antimatter too, because matter and antimatter are both created, and one of them there's a little excess, and we call it matter. Okay, so you're really it's hard to envision what's happening at 10 to the minus 40th seconds, but there is something else down there we call the Planck's length and the Planck time, and they are the way I teach size of the universe is it's bounded on two sides. If we go back in time, we cannot get past 10 to the minus 46 seconds. I think is about right order of magnitude. That's when the uncertainty principle from quantum mechanics has to be invoked to say you can't know anything smaller than this. And there's also a Planck time that goes with it. Again, 10 to the minus 43rd seconds or so. So the universe is beginning in a place that is hidden from us. Okay, and where it's gone, at some point in there, it got bigger. It got bigger than we could ever sense. We don't know how much bigger. We just know it's big enough that we think that if you went over to the edge of the universe over there, you'd see exactly the same thing of yourself being in the center of an expanding universe, no matter where you are. So yeah, very interesting to think about being on the edge of that expansion, but we have no data to tell us which way to look.
So you can't say that we're at.
We can talk about the edge of observable.
Light.
Okay, and that's the world we live in. And you know, many of these things are nonsensical at one level, maybe at many levels. But they have data behind them that we can't come up with a better explanation. Oh, by the way, if you can be the next Einstein. It's egalitarian, open to everybody. You know, the thing that is still so fascinating about relativity and Einstein is he's one guy working by himself. Okay, no, he did have other people, but you know, it wasn't, you know, NASA. And he came up with something that changed our universe completely because he asked a basic question: what happens to Maxwell's equations as you get near the speed of light? Okay. And then he could express it mathematically, which is the most amazing. So last, you know, again, textbooks are your friend. General astronomy textbooks are your friend, as are, well, what was the interesting one in this one? Oh, this is the Wolf-Rayettes. Oh, and they also do Cepheus. Oh, that's in the sky. Come on, there we go. Give me a nice picture of a Wolf-Rayette. What is a Wolf-Rayette, she asks. They're stars that have thrown off all the matter and there's nothing left but the actual core of helium burning in fission. They're just amazing things. So again, I can't recommend the publications simply because you stick one of those in the back of the toilet, you're going to end up learning things. Okay, that's where I learned about beryllium. Was I had an issue and I think I let the subscription lapse, so that sat on top for like 3 or 4 months before I finally understood that the cosmic abundances, lithium and beryllium, are all from cosmic rays. And that proton thing just clicked and said, yeah, for some reason they're not favored. And if they were, our world would be very different. But does what?
You need more roughage in your diet.
I eat shredded wheat. Okay, I've been done for a while. You know, we may
Just a reminder, we got an open house on Sunday, 10 to 3. We might do some solar observing if conditions allow. Thanks, everyone.